Okay, friends, Saturday, 8:30 p.m. in Indian Standard Time, and we are back, uh, back for the webinar, the series, mega webinar series, Saturday Manufacturing Talks. As you know, the Saturday Manufacturing Talks is getting organized by the Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. And Center of Excellence in Advanced Manufacturing Technology is industry academia collaborative research platform. We do have a consortium of the several industries, presence of both public sector and then private sector, and we do have also presence of the startup. So we are working closely with the industries, spanning across the different areas of the manufacturing. Now, the Saturday Manufacturing Talk we are organizing since March 2021, 13th of March more specifically, and today is the 39th week, December 4th, 39th week. The last week we had the speaker, renowned metallographer George Vanderboot, but the webinar could not conduct that one because he got hospitalized. But the good thing is that he has been discharged from the hospital, and then we have already scheduled his the webinar sometime in the January. Anyway, so in this webinar series, we are discussing about the various aspects of the manufacturing. We are fortunate to have speakers from industry, academia, and both from India and the rest of the part of the globe. And today we are very fortunate to have Dr. Supriyo Ganguly from Cranfield University. Dr. Ganguly is presently a leader in welding and additive material science in the welding engineering and laser processing center. He is also the director of the Masters in Welding Science and Metal Additive Manufacturing courses at Cranfield University in the UK. Supriyo is a material scientist, and presently his research is focused on wear plus arc additive manufacturing (WAM), and also he's the keenly doing the research in the field of the laser processing, joining, and surface modification. He's a very prolific researcher in this field, and is having a lot of the international publications, close to 100, and with a very high impact factor, the H index of 27. With this brief, the introduction of Dr. Ganguly, I request him to provide with this, looking forward.
Thanks, Professor Paul. Now, if Ananta gives me to share, then I will start sharing the slides. And before I start, actually, I want to say thanks for the kind word, and it is indeed an honor and pleasure to talk to you all. And I am very happy to present today the work that I am started to do like few years back in the area of wear plus arc additive manufacture, and as Professor Paul said, I'm very much into laser welding and also advanced arc welding processes. So without saying any more, because this presentation contains some of the introductory thing that I want to say, so I will start talking about with a brief introduction of our university and in particular our center. Then I will give a short introduction to wear plus arc additive manufacturing, and from there I will show some of the critical structural alloys that we are working on. On this regard, I want to explain that all these different alloys are in different technology readiness level. Like titanium, all the wear plus arc additive manufacture was practically started with titanium. I mean, the full thrust came on this particular manufacturing route because of titanium and its incorporation in the aircraft and aerospace structural product mix that started like 15 years back in a quite massive scale. And the the manufacturing routes needs to be redefined because.
Yeah, Dr. Ganguly, would you mind changing the display settings a bit? Yeah, so that only the main slide comes up. Yeah, great,
Okay.
great. Yeah, good, great. Please go ahead.
So thanks very much. So I will. So the main point that I was trying to say is basically titanium was being researched for, or is being researched for a while now, whereas slowly the importance of this particular manufacturing route is understood in all different sectors and realized the potential of this. And I will give some glimpse of the work that we are doing in, say, aluminium and high strength steel like managing steel and all. So firstly, I will talk a little bit about our university, which is located about 50 miles north of London. And it is in a strategically very nice location because it is in the skill corridor between Cambridge and Oxford, which is defined by the present UK government as the area where there will be a lot of activities in terms of high technical, high or advanced technical research, this particular area. So we are located in strategically very nice place. A slight introduction of the history of Cranfield. So originally it was Royal Air Force after the Second World War and became College of Aeronautics in 1946. A picture from there is shown at that time. And in 1969 it became Cranfield Institute of Technology, which and given the charter to award university level degrees. And in 1993 we became Cranfield University. And so there are the distinctive strengths. As if you see the left hand bottom corner, the distinctive strengths are in the aerospace, defense and security, energy and power, environment and agri-food, school of management. We have a very famous school of management, manufacturing. So this is where we actually lie within the university. We are within the part of the manufacturing theme. We call all these as themes: transport systems and water. So we are part of the manufacturing thing. Cranfield University is an applied university. So our basic strength, we are postgraduate and applied. So our basic strength is in doing very industry focused research across the different TRL levels. So by TRL, I mean technology readiness level. So at a very low level, it means there is an inception of a concept or something. And whereas at a high level, it is basically ready to be used or for a particular product or service and things. So we are just as in the top 40 in the mechanical, aeronautical, and manufacturing engineering area, with unique facilities such as Aerospace Integration Research Center, Crash Impact. So we have a secured site, National Wind Tunnel. So all these areas are give or allow us to do very focused research with the practical application and the service condition that a component structure of or a functional element is subjected to. So you can now see the new picture of Cranfield on the bottom right hand corner. So we have a airfield, and this is one of our very kind of unique facility that we have in our university. So this short video will explain you the different types of work that we do, and I believe you can hear the voice.
We can see the video, yeah. Voice is not coming up, but see the video.
So this gives you a basic glimpse of what we do. I hope the sound was audible. So now we are here in the red rectangular bracket I've shown, or box I've shown our center. So we were founded in 1961. We are going to celebrate our 60th anniversary next year. We have over 600 alumni in the area of masters and PhD. We have about 7 academic staff, 3 technicians, about roughly 10, but so sometimes it varies basically. So I would say right now it is about 12 postdoctoral research fellow. We have about 15 PhD students at a given point of time, and roughly 16 full-time equivalent master students doing welding. And now we started the IIT manufacturing course since 2019. So a basic glimpse of the lab I will give you here. This was done by a student basically using his drone. So it is it will just show you the scale of the lab we have. So this is a lab which is situated over 700 square meter, and it is completely open architecture. And it is not like we have some particular instrument which we use to produce some research in one direction, but we set up and manage to do things as we need or as we go, and depending on the project. So in the area of arc welding, laser welding, and IIT manufacturing, or bar plus arc IIT manufacturing, we are really quite internationally leading at the moment because of this huge facility, and that brings us very close to the industry because we allow doing stuff in a level where industries feel very confident or comfortable. So this is a brief introduction to our lab, and now I will start talking about where plus arc additive manufacture. So this is just comparing with what is people do conventionally, just with a sculpting concept. So in normally or traditionally, complex parts and shapes are machined out from a block of metal, whereas in additive manufacture we built it layer by layer. So this is the basic difference, and that gives us the enormous opportunity to save material and to do things which are not quite possible in traditional manufacturing. So this is the basic difference between additive and traditional way of manufacturing a component. And now I will talk about a little bit on the metal additive manufacturing. As you can see, metal additive manufacturing is in existence for quite a long time, and traditionally high power density beams are used, like laser beam or electron beam, and with a variety of configuration. It can be laser plus wire or laser plus powder, and laser plus powder can be done in different ways, like powder bed or blown powder, and accordingly they call different names in their, or terminologies in there. Similarly, electron beam welding also can be done with powder or wire and powder bed, and electron beam plus wire can produce very fast, or the productivity is quite high, which is known as the Sayaki process. We profess in this area, which is using arc as a power source, and this can be either traditional GTAW welding or a MIG welding or a plasma welding. Whereas we found that plasma is probably one of the most attractive power source because of the high arc length that plasma can generate, or plasma offers, and which gives the flexibility to add material in it much better than a TIG process. Now, TIG and plasma are essentially same process, where we can control the heat input irrespective of the wire feeding, or it doesn't depend on on how much wire we feed. So the wire feeding rate and the power input or the heat input from a process are decoupled. Whereas in GMAW or MIG process, this is basically coupled. So that is one of the disadvantages of MIG process to do very high-end job, but MIG can be quite good for different types, other type of process. Particularly, we are using MIG and we use cold wire. So cold wire MIG basically to generate very large scale structures, and there the cold wire which is fed into the arc or into the weld pool is basically used to control the heat input, and the cold wire feeding can be controlled independently. So we are trying to bring GMAW process as a it is quite easy to control, and the wire is the electrode, so wire feeding is central. There is no direction dependency and things like that, so which makes it quite a nice process. With all these welding processes, we use wire, and that's why we call it wire plus arc additive manufacture. So this is an example of a powder-based process where a turbine blade is manufacture of a turbine blade is schematically shown. So you can see that we have a powder bed, and on which laser will be impinging or irradiating, and the powder bed will be lowered, powders will be fusioned or fused, and slowly you will manufacture what is known as a net shape component, or you really don't need to do much machining or any machining when we generate such kind of component. So it creates a a component which can be readily used. So the material utilization can be quite high, although there is loss of powder during the process. As you will see that after manufacturing, the product needs to be cleaned, where it will be surrounded by powders, and once the powders are removed, you have a net shape of a blade or any component that you are manufacturing. In case of wire plus arc additive manufacture, it is slightly different. As you can see on the right hand top side, once again an animation is shown of a aircraft landing gear rib, how it is deposited layer by layer, and there are different strategies. Actually, I will say briefly about them, but the control of the thermal stress is extremely important, and often we do things where the substrate becomes a part of the component. As you will see here on the left hand top side, we are not making two components, we are making one component, but we are using or we are flipping the the neutral axis was of the component was done separate in a manner that the substrate on which it is built become a part of the main component. On the right hand top side, a plasma arc is shown, how the material is fed, and on the bottom side you can see that a component, a proper component which is was manufactured, it is made of titanium. A lot of work has gone in to understand this process, and the next few slides will talk about that process basically. But before that, just to give you the scale of saving that you can do. So in a traditional process with a billet and taking out all the materials, it will be extremely expensive, because the cost of titanium can be quite high in its rod state, and the cost of scrap titanium is practically nothing. So basically, it is a huge amount of material saving that this manufacturing route offers, makes it so attractive to all the high-end manufacturers where people use titanium and stuff. And needless to mention, titanium machining is a very difficult process. It is not straightforward like aluminum. So from that perspective also, it is a fantastic process for titanium. And as I said, initially most of the research was funded from people who are planning to use titanium into their product mix and want to have a process which gives the best yield and lower material wastage. So I will talk about a little bit on the different structural alloys that we are studying now. Just to give a brief context on this, wire plus arc additive manufacture basically relies on successive deposition. And as you are quite, as you can see in the components even, we call it near net shape. It is not a net shape component because you need to do machining before it can be finally implemented. However, the process itself is results in several thermal cycles. When a layer was deposited, as we keep on building, it will have several thermal cycles, and it would obviously depend on the geometry of the deposition and how much is the energy input that is going through each layer. So this will result in a differential thermal profile in a component, depending upon whether a layer was deposited at the beginning or towards the end. It will have quite different properties, or it might have quite different properties that I will show you in some of my work. So, and also because it is cooling from liquid state, it will give segregation of solute atoms, which will therefore make it even complicated for heat treatment and things, because say for age hardening alloys, where solutionizing is a step before we go to aging process, and solutionizing might not be very smooth or uniform throughout the whole component if there are a lot of segregation. So this particular presentation will focus on the response of different alloys to the deposition thermal cycle and ways to mitigate some of the issues which I will talk about, and how control of thermal mass is important in order to generate a structurally a component which has good structural integrity. And by that I mean basically there is no defect. That is what I want to show you. We can use this manufacturing route as a I mean, this manufacturing route offers a lot of flexibility. So we can manufacture multi-alloy material, or even we can mix wire to modify composition in particular areas. So some of the work that we are doing in this regard will be shown. And in order to avoid the elemental segregation, what we are doing now is cold working. So once we deposit a layer, we cold work on it, and we use generally two processes now. One is rolling, which can be done fastly on straight lengths, but if there is a curvature and things, it can be very difficult. But then there is another tool of cold working, which is pinning, and we are also now doing a lot of research in how to pin a component properly using either machine hammer pinning, or it can be ultrasonic pinning. And afterwards the deposit microstructure was basically ready for further heat treatment in case of alloys which needs heat treatment, like as I said, age hardening alloys. So I will exemplify it in my merging steel study. So deposition strategies. So what are the deposition strategies? So this is a example of a sparse kind of a structure where all the different types of deposition principles were shown. So this bit was produced by single pass, which basically means we are doing just one layer and then build on that single layer. Now this deposit what we call a parallel pass, so which is shown by this dot is basically the start point, and the arrow shows the directions, and it shows that we built passes side by side in order to produce one layer. So in order to make it a bit more thicker, basically. So single layers are obviously less thicker as compared to parallel depositions. And then we have oscillation. So oscillation is basically it creates, as you can see here in the schematic, it basically the torch moves and in the transverse direction. So one layer can be quite large. We can control it as much as we like, depending on the size or the geometry of a component and how we want to deposit it. So this is some example of the process. So which is quite is to see here how the weld pool changes when it comes to a junction, or when it comes to a place where the thermal mass is very different. And at steady state, everything can be quite nice and good, but one of our expertise, or where we really made a very significant progress, is to understand how to deposit when the thermal mass changes. And as you can see, when the weld pool shrinks, because the thermal mass is larger now, it will definitely generate defects and geometrical inaccuracies. So this is an area that we are focused on quite heavily and studying. So based on the deposition stats, I don't know why this. So this is a change in thermal field near the intersection, which needs for compensation. This is another example of the work that we are doing. So this is a single pass automatic wear position adjustment. As you see, the surface tension of the weld pool changes as it progresses, and it is quite normal, because as it moves, there is heat accumulation, and as a result, the temperature of the weld pool basically changes. Now, in this particular example, we are trying to show that we have developed processes through which the distance between the wire and the relative position of the wire to the arc remains constant throughout a deposition process. So these are the different areas of process studies that we have performed, and generation of components really needs all the very clear understanding in these areas. The next few slides, I will try to show you the different, an example of forming a cruciform. So you can see this is a cruciform, the dimensions are given. The most important thing is how to manufacture this. So this is in option 1. It is just like a reverse tool path approach. So we start building from the middle, and slowly it goes out, and we use the same parameter set and everything. So now you can see the component, which is really completely riddled with defects and stuff, and the layer height is completely inaccurate and things. It is because the thermal mass of the depositing mass is continuously changing, and unless these are addressed, it will never be able to generate a structurally sound component. So now there are some segmentations were done where the deposit parameters remain same, but the tool path was changed. And here also, as you can see, there are some inaccuracies and some defect, although it reduced to some extent. Now this is the other part, so which is the final part building, which was done here, where we managed to rectify all these defects and all the resulting, the parameters and all the resulting defects. And here it is showing, as you can see, that there is segmentation and zoning in the toolpath. So the different colors are showing that the speeds and stuff are changing, and the multiple sets of parameters are used. So once this was done, it managed to create a completely sound cruciform, and with target layer height in every aspect of the deposit. However, the thermal effects can still be seen at the edges, which you can see here. So how do we control material properties in WAM? So deposition path and the control on the thermal mass. So here once again I would like to show show the same slide, basically, where, just to recapitulate, the single pass, parallel pass, and the oscillatory deposits, as you can see here. And the next slide will show you the resulting mechanical properties that are coming from there. So you can see here on the left hand side, I will concentrate at the moment. So you can see here this the red one is basically oscillatory, and the circular one, the black one, is a single pass deposit. You can see here the parallel pass deposits has significantly larger mechanical properties or significantly higher mechanical properties as compared to the single and oscillatory deposits. In fact, oscillatory produces the least amount of or the lowest mechanical strength, whereas the parallel gives the maximum and the single pass is somewhere in between. However, all of them are quite low when we consider a wrought alloy plate of this particular alloy. So this is, we are talking about titanium 64, which is probably the most used titanium alloy in the titanium family of alloys. So a detailed microstructural study was carried out, which I'm not going to talk here, but I can guide you to all the different papers at the end, which will show the reason for this variation, where the thickness of the alpha lamellae, which titanium 64 is a two-phase alloy where the most of the part is alpha and there is a small amount of beta or some amount of beta. So it was shown that the thickness of the alpha lamellae and the size of the alpha colonies are basically responsible for the differential strength that was generated in the different building strategy. So this is why I'm showing this, is basically to emphasize the fact that it is important to understand the microstructural variation that would generate from the different deposition principle, as well as using different parameters, and from the thermal mass that would be different in different areas. So to create a homogenized component with uniform properties, low anisotropy, and all these, it needs further work to be done. And the next few slides are basically showing on that. So in titanium, what we are doing, titanium 64 is a fantastic alloy for this purpose actually. So the top left-hand slide is basically showing the rolling process that we are adopting now during generation of this kind of part. And the bottom one is basically showing the actual part, actual structure building that was done in this study, which we are showing now. So every layer, once it is deposited, it was rolled, and therefore what happens, there is some amount of, and it was rolled at room temperature or close to room temperature. It is not rolled hot. So what happened, the thing is cold worked, and when the subsequent layer comes, it will show, particularly because titanium 64 is a two-phase alloy. So over like 880, it will convert to beta phase, and below it will be alpha. So there will be, so this particular wall that we are, if you can see my mouse, it is showing that the large kind of epitaxial growth of the grains that you can see in the wall, and the EBSD image is shown on the red one, which is on the right hand side. And then when we do a rolling of it, and we can vary the rolling load actually, when we do a rolling with 50 kilonewton, this is showing the prior beta grain size which was generated at high temperature, which then formed or which then resulted in the alpha grains. So as you can see, the prior beta grain size when rolled with 50 and with 75, there is a significant reduction. So basically, it is possible to control the grain structure of such deposit through application of cold working. So this is the kind of work that makes it possible to bring this technology close to the manufacturers, because it is possible to get strength close to the wrought alloy. So this is now what I will be showing. So this is basically different types of roller we tried, a profiled and flat roller, and you can see the different levels of grain refinement that can be achieved as compared to the extreme left-hand micrograph, which is showing just dendritic epitaxial growth of grains. So now I will talk about the the directionality or the anisotropy that you will see when the grain structure is completely aligned to the deposit directions. So if I go back to the previous slide, so on the left hand side micrograph is basically the strength that you are getting from that is shown here in the filled black and the empty black circles, where you can see there is a very significant difference between the two directions. So the vertical is always lower as compared to the horizontal, and then there is a significant difference between them. Now, when we roll it with 50 kilonewton, as you will see, the difference in the strength or the differential strength between the two directions is now quite less. And when we rolled it with 75 kilonewton, as you will see on the top side, it not only exceeds the wrought alloy strength, but the anisotropy is more or less eliminated. So this is basically a kind of a situation where additive manufacturing is proven to be, with necessary processing, is proven to be a very suitable technique to manufacture components, because not only it creates a structure which is completely isotropic, but it manages to generate strength which is more than a product which is coming from a mill. So this is showing the average values of the two sides, and as you can see that the 75 kilonewton rolling is basically even with any process. So the two processes were studied basically, but plasma and TIG, and both the processes generate strength which is higher than a wrought alloy. This is one of the area which we like to which I would like to highlight to you, that how the static properties can be controlled in additive manufacturing process. Then the next area which I'd like to talk about is control of composition. So additive layer building gives us the unique flexibility of adding materials as we like. So in this particular work, so this was done by one of my students a few years back. So here we added tungsten carbide powder in the melt pool. So this was done by a GTAW process, as you can see, and I am adding wire and also powder, and that gives us a kind of a composite structure which looks like this, which is very much acceptable to the industry for whom I was working at that time, from Cranfield. So this is a kind of a structure which was produced. So this particular application was in railway brake disc, where two properties are extremely important. One is thermal conductivity, another is abrasion or erosion resistance, because when a brake disc engages with the clad, it generates a lot of heat, and unless the heat is quickly carried away, it will deform. And also, of course, the process, particularly if there is a emergency kind of a situation, it will cause a lot of frictional force in the interface, and as a result, it can worn out pretty quickly. And tungsten carbide will probably give us strength to lowering that the erosion behavior, or lowering the material loss. So different materials were studied. So you can see here tungsten carbide with the wire gave much higher hardness as compared to we tried with silicon carbide also, and that is shown in the black. So controlling composition with multi-wire approach. So this work was also done by one of our students a while back, because it was in this one. This was basically the root of it was the first seed project, we can say, from which we had this concept. So he added this multiple wear in order to avoid solidification cracking, because what happens in some of the aluminum alloys, solidification cracking becomes inevitable because of the solidification path and the phases that forms during the solidification process. and there's a huge certification range which results into that. So this multi-wire approach was actually done in order to get rid of the large certification range, or rather, to say in other words, to modify the certification path in a manner that the certification range becomes very small, and therefore to avoid certification cracking. So this particular work was then taken forward further with addition of a third wire, because in that case we can have a deposit which is as strong as probably the parent metal. So which is one of the major issue in aluminium, that the weld metal is and the associated heat affected area has quite low strength as compared to the main parent metal. And now this is being controlled by adding several wires, and this particular principle is taken for development of additive built aluminium parts. So you can see here that wires are being added, but this is an example where it goes wrong. Basically, if you see what I mean, you will see that there is a crack formation that happens during this process. Whereas when things go right, it can be quite nice actually. So then the deposit and things can be built quite with a lot of integrity without much formation of cracks or internal defects in the deposit. So you can see here that we are trying to mix aluminium lithium with aluminium magnesium, and the target composition is shown here, that we wanted about 1.8% lithium and 4.5% of magnesium. And this is why this is being tried, because we found that aluminium magnesium lithium alloy family can give you relatively low density, and the lithium gives or increases the specific modulus quite significantly, which is Young's modulus divided by the density is quite high when we have lithium in the mix, and potentially insensitive to pre-stretching and quenching rate, which is enormously beneficial for AM. And the different weight percent of composition, if we know of the wire, then we can generate a target composition by controlling the feed rate of the different wires. So this is basically exemplified in this particular work. And just to let you know that these works are done to do the research on how the composition can be adjusted, or what to get an optimized composition for a particular type of application. And then we work with different wire manufacturers. So this type of wire can be manufactured to the specific chemistry, so that we don't have to mix, or in practical applications, you don't have to mix and use a relatively straightforward process in order to generate a deposit. Then also we are now trying to develop aluminium copper lithium magnesium alloys, so which will reduce the certification cracking sensitivity and relatively high mechanical properties. And so copper is added to reduce the certification cracking behavior, certification cracking tendency, and magnesium will generate sigma phases, which are, omega phases, which are quite important to improve on the mechanical properties of this. And it generally doesn't get overage, so aluminum alloys, one of the major problem is overaging while you generate the while you weld or do any kind of processing with heat, with thermal energy. And this particular phase is quite strong, and it tends to overage quite less actually. So how it can be achieved? It can be achieved by mixing of 2395 wire with which is magnesium 9% aluminium with 2319 and aluminium 2% lithium wire. So these are the tentative compositions that can be achieved with different wire feed speeds that are shown on the right hand side. So control of composition with mixing, so you can generate, so these are some examples of different types of structures that can be generated. So this is a iron copper structure, mixed structure. We can have inverse steel wall, where the load carrying capacity increases. One of my students has done some work in the area of refractory based alloys, and a graded structure with tantalum, molybdenum, and tungsten were shown here. This work has been published and you can access it quite easily. It is in free domain. So control of properties through rolling. So aluminum also one of the major candidate for cold rolling, and you can see here in as deposited condition how the size of the grains are changing, actually the mean diameter of the grains, and you can see here that the nature of the grains were changing with lowering of the texture and lowering of anisotropy. These are the different grain structures that you can obtain. So only rolling, you can see you can have pancake shaped grains, but after heat treatment it forms a equiax structure. This is a very interesting observation with aluminium. You will see here, because these are all age hardening alloys. So basically after whether it is from a mill or whether it is through this process, you need to do a heat treatment, and the heat treatment is it can be done at T6 heat treatment, which basically means artificial aging. And you can see here that the cold work, which is once again the circle, the black circle, and cold work will increase the strength to some extent, and cold work plus artificial aging can take it to over a strength which is more than the wrought alloy. You know, the wrought alloy was shown by the green triangle, and you can see here that the strength has increased tremendously. However, when we do artificial aging directly without doing any cold work, then also you can achieve the similar level of strength. And this is a very interesting observation, as you will see in the next alloy that we have studied. I will show you that it will be very difficult to get the same thing in maraging steel. Therefore, of course, it depends how the aging process work, or what are the characteristics of the precipitate in the aging process that actually determines whether it can be achieved directly through aging, or you have to go through the cold working process. And this is aluminum 2024. A very similar observation was also seen. So 2000 series aluminum alloy can achieve its peak strength without any cold rolling. However, cold rolling can be extremely important to reduce porosities and other sorts of defect that normally accompanies in aluminum deposit. So and also a cold roll structure generates much more or much better ductility or toughness as compared to a directly aged alloy. So in those respect, cold rolling can be a very important aspect that should be followed in aluminum alloy as well. So I will talk a little bit on the maraging steel study actually now. So material properties. So there are 3 grades of maraging steel generally available in wire form, and you can see here that there is a high nickel steel with basically moly cobalt in its mix. The moly is basically primarily responsible to forming the edge hardening, because maraging steel is a very clean steel. The carbon is almost close to 0. I mean, much less than 0.03%. So carbon doesn't impact or influence the strength of the martensite, basically. So when this maraging steel is formed, it generally at normal cooling, it generates martensite, and the strength is quite low actually. And then when it ages, it forms precipitates like Ni3MO or something, and that gives the strength. And this material can generate tremendous amount of strength, and because of the nature of the precipitates, it is quite like it generates quite isotropic strength. I mean, the strength is not dependent on the direction or anything, because the precipitates are quite spherical in nature, I would say. Just a little bit about this alloy. So molybdenum is the main hardener, and it hardens the matrix to formation of Ni3Mo kind of structure, whereas titanium is a secondary hardener. It also forms Ni3Ti in this, and when it is aged, in further aging, it is Ni3Mo is dissolved and Fe2Mo also forms, which also adds to the strengthening behavior. Cobalt was alloys mainly to lower the solubility of molybdenum in martensite so that it can age efficiently, and the coherency strength of this type of alloy restricts the growth of Ni3Mo type precipitate. These are the few physical metallurgy bit that is important, and also what is the in this particular composition. So the heat treatment will depend on this. This is the metastable type of situation which we normally face, rather than the right hand side, which is the equilibrium. So there is a slight hysteresis between the austenite reversion and austenite and martensite formation basically, and that is important for heat treatment of this alloy. So we have studied these two particular grades, 18 nickel 200 and 18 nickel 250, and this is basically we have to form this. You cannot see it clearly actually, but this has to be done. This particular deposit has to be done in an inert environment. You can see on the right hand side a little bit of the thing. So this is a kind of a transparent tent. We called it Huntington shielding, which we developed through some of our suppliers in UK. So it's basically a large tent, and I mean a kind of a polythene plastic polymer built tent, and it can be inflated with argon, and we have it is like act like a glove box where there are access to this kind of setup if you want to change something. And it is very important actually in this, because you cannot really build such kind of structure in normal environment, because the scale formation or the oxide formation while you build will be tremendous, and that will change the surface tension of the weld pool and will impact how the scale will be either entrapped within some of the part of the metal, which will increase the strength but reduce the ductility tremendously, and there will be uh, lot of influence on the property if it is done in normal shielding or normal environment, which is beyond the control of an operator. So now the interesting thing is in margin steel is, as you can see, that as we keep on depositing, we are aging the steel basically. So the deposits which are done at the beginning are aged slowly with the layers that were deposited. So the black curve is showing that near the top, the hardness is quite low, whereas after a certain level, the hardness jumps up. And that is because of the fact, but this aging is kind of a incomplete aging. It is not a full-blown aging. And when we take this whole structure and do the actual heat treatment, which is solutionizing and aging, then it jumps back to the level where it should be roughly. However, I will show you that it is still not enough because of the solutionization process now is quite incomplete, and therefore this particular type of deposit will never achieve its optimum strength without any kind of mechanical working while depositing. So this is some of the microstructural studies that were carried out to show that the proportion of retained austenite at different levels of the deposit, and this is basically shown here in this particular micros, and also associated segregation. You can see here the molybdenum and titanium segregated. So some ACM work was done, and to understand why the aging response is not as good as, say, the aluminium, because these are quite heavy atom and its diffusion of them is not quite straightforward. So now I'm showing the left hand side, the two micrographs. That the left hand side top one is the micrograph taken from the top in as deposited condition, and the bottom one is from near the bottom of a deposit in as deposited condition, and the right hand ones are the same thing after heat treatment, and it is showing some amount of precipitation actually after the heat treatment, and that's why the hardness has jumped up. Then a study was performed to understand the different proportion of the intermetallic aging precipitates that are forming in the different areas in as deposited and aged condition. And it was shown that the Ni3MO breaks and Fe2MO grows as we do the heat treatment. So the different alloy compositions or the different aging precipitate concentrations were studied and is shown here. But most importantly, so this is the kind of tensile test, number of tensile tests in horizontal and vertical directions were carried out, just to show you the amount of testing. So were carried out for this. So the red ones are heat treated, and the other ones are in as deposited condition, and we have done to cover the entire length of the wall or the build direction and also vertically. Now this is the kind of the left hand side is the horizontal tensile strength results, and the right hand side is the vertical ones. As you can see here, the heat treated ones has gone up quite significantly strength wise as compared to the as deposited ones, so which is quite expected. However, it never achieves like 100% of the wrought alloy strength. It is like if the strength is like 1700, it is coming to about 1500 or so. So in as deposited and heat treated condition, this steel or this alloy fails to achieve the maximum or the optimum strength, and that is here we have averaged out sorry, in this particular graph we are showing the elongation, and it can be seen that with the heat treatment the elongations are primarily reduced, or the area under the tensile curve is reduced. So this is basically shown here, and you can see here the different strength that are mentioned here. So in as deposited condition, say the horizontal it is 1118, and as deposited vertical it is quite low or quite less as compared to the horizontal, which is quite expected. Actually we found them like this. And unaged wrought, which is basically wrought after without any aging, is even less than the as deposited ones. Whereas when the wrought is aged, it has gone up to 1450 and 1760 in case of say 250, whereas in my case it is 1410 and 1345, so which is significantly less as compared to the wrought alloys. And I'm using a wire which is close to the composition of 250. So now what we have done some mechanical working which is very similar to the previous ones, and this is basically showing it was done with a flat roller in our there was a CNC gantry system which is now removed with another new rolling unit, and we have done the rolling, interpass rolling, so every pass deposited and then rolled, and it is basically showing here the impact of the rolling. So the unrolled one has completely elongated grains as you have seen in case of titanium and all, and while the rolled one is now started to show the high angle grain boundaries that we like to see in these deposits after rolling. Now how it is important is basically will be shown in the next slide, that this rolling then allows the thing to age properly. And why? Because it allows it to solutionize properly. Now you can see here this unrolled horizontal and unrolled vertical, which are shown here by the red and the blue marks. And see here, I will take these triangular ones, so 50 kilonewton aged and 50 kilonewton age horizontal and vertical. It has now achieved to a level of the wrought alloy, which is shown by the green star. Is basically, you can see here, and these ones, which is the empty circles, the red and the green, blue, they are basically the as deposited and aged ones. So what I'm trying to convey from here is cold rolling is an extremely important tool in order to allow the matrix to be solutionized properly, and therefore its aging response increases tremendously. So this is a work which is being done in this merging steel, which shows that even in this kind of high-end alloys, it is possible to get or possible to maximize or achieve the optimized strength and toughness by implementation of cold rolling, which is a very important tool for wear plus arc additive manufacturing. So now I'm showing you the result of the work. So you can see here the rolled with 50 kilonewton or 75 kilonewton both have very similar effect actually, and here we have achieved the strength, which is 1750 and 1751, and which is very close, I mean, which is practically identical to 1760, and therefore it managed to get the same type of strength as the wrought and aged alloy. So this is some further microscopy work that the student had done just to show that the rolling generates the dislocation clusters, which help in getting the with the next layer deposition. It then allows it to get a formation. I would not say recrystallization, but I would say at least partial reformation of the grains, which are quite effective in achieving the solutionization which is required afterwards during the heat treatment. So these four figures are basically showing that if you see the top one, the intensity or the strength of the intensity is 15 times than the random texture, whereas the bottom ones are showing with different levels of rolling, it is now reduced. So basically the alloy is now becoming much more isotropic and without much of texture. This is a showing of the grain structure that on the right hand side is basically of the rolled one, and you can see here it is kind of the texture is becoming much more randomized. And this is the structure after heat treatment. So where the precipitations are quite clearly shown, some dislocations densities are also can be visible. Okay, so that is bringing me almost to the end of the presentation. So this work is quite significant towards the development of CoEAMT as a very important tool for manufacturing of high-end alloys. So it is possible to deposit and create structure using the latest power sources and necessary atmosphere control. So following the principles of precipitation hardening, and as depositor structure showed hardness and strength in between the solution, so which I was just saying actually. So you can age as depositor structure, but you never receive or never achieve the maximum strength that you can do using rolling. So we identify that probably the lack of high angle grain boundaries, lack of dislocation density are not conducive to solutionize the structure to the extent that is possible with rolling basically. So cold working obviously gives the necessary grain structure reformation, introduction of high angle grain boundaries, which will allow a proper solutionization and thereby the response during aging will be much better. So overall summary, I would say it is possible to achieve deposit strength close to or exceeding rod variant of different alloys. Segregation and epitaxial growth in this manufacturing process is an important issue, and interlayer rolling could be an effective tool. So this particular manufacturing technique, WAM, offers excellent flexibility towards modification and tailoring of compositions. So design of deposition process is important to change the to address the difference in thermal mass, and this is important because the microstructure and the mechanical properties needs to be or inherently linked to the thermal profile of a deposit. Here are some of the references that were published from these works, and we are still publishing and doing a lot of study in this area. Rolling is quite a complicated process, so we are now studying pinning, which I said ultrasonic pinning is, and also machine hammer pinning. All are robotic that we are trying to implement in order to generate the necessary microstructural modification that we obtain from cold rolling. So this is the whole. We have a large WAMAT program, and Professor Stuart Williams is our chair in the center. So these are all our students, and now they're working as research fellow or in different places, and they're all works are basically shown, and this work is ongoing actually. So thank you for listening, and if you have any question, please let me know.
Yeah, Dr. Ganguly, I mean, thank you so much for the detailed presentation, detailed work of in the field of WAM. We are amazed to see the high-end infrastructure that we have at Greenfield University, the field of the building and then so the WAM. It's really wonderful. You have mentioned about the thermal mass. It increases with the deposition and all. So and thermal mass, it's a critical factor because you have rightly told that it controls the microstructure and then by the mechanical properties. So do you think any possibility, or let's say if the possibility does exist, how to control real-time monitor the process, and then how to control the process parameter in the real time? How difficult it is?
Yeah, it is actually, I would say, the majority of the research is now focused in that area, that how to control the cooling rate of a deposit, and I've just been the internal examiner of a student called Alex. So he actually did some really good work. So what is happening now, we are trying to use wavelength corrected pyrometers, to measure accurately the whirlpool temperature, and from there we're trying to control the deposit parameters. As I said in the beginning, like plasma and TEAC are two processes where you have the wire feeding and the current are independently controlled. They are not controlled. They are not coupled. So whether dynamically, when we see that the temperature is rising, whether it is possible to reduce reduction of the current has different implication also, because it will reduce the magnetic force and things. So basically, if you can increase the wire feed speed, as you can see in some of the controls, that by monitoring the whirlpool height, because it is also changing because of the change of surface tension. So how to say either increase the wire feeding or lowering the wire feeding position. So all these things are being performed actually, and these are very much all are under study, so people are trying to build models to understand that even before a part is built, what will be the implication, and there are softwares that are developed by, there is a spin-off company called WAM 3D, which is where Filomeno is basically, he's the CEO of that company. He's gone, he's toward, and we have some other people who are extremely in the process. So they are trying to work with that how best to control the thermal profile. And you see, I mentioned about cold wire MIG. So that is one of the process which becomes very, very favorite, because in cold wire MIG you have the complication of the wire feeding is much less, because the wire is feeding centrally, because it is a part of the electrode, and the cold wire feeding can be controlled much more easily, in order to, and it will give you control on the temperature of the weld pool, which can be independent of the actual arc power and stuff, other things. So these are all areas which are being studied actually at the moment, and it is like kind of a different principles are being implemented. It is not like one principle or one factor will solve all the problems here. So
you have mentioned about the in fact, I must say that's a nice work that after warm you are doing the cold rolling, and then trying to improve the quality. And you have given example for the different grades of the titanium Ti-6-4 and the Ti-6, and also the managing steel and all. So do you suggest the cold rolling would be required after warm for all grades, or I mean all type of materials, or is it?
and I mean, it all depends. Say this famous saying, horses for courses. So we have to see what is the application requirement. And of course, if you have something like aerospace, and where it is quite safety critical and stuff, so it is really important to uh, do the cold rolling, in order to reduce the anisotropy, formation of kind of high angle grain boundaries, which will make the structure, I mean, which will make the component structurally very sound. So that is, cold rolling is a really good tool, but how to implement that is still a lot of debate is going on, because I mean, pinning is a tool which I haven't shown it actually, but pinning is a tool which can be done online. So you do a deposit, and then there are robots now in our center which can I mean, which has two kind of holders. So one is depositing, the other is coming and then pinning, and and in the next pass it is once again depositing. But the range of, I mean, I haven't seen a pinning tool which can really do a depth of deformation as good as rolling. So that is one of the issue. But rolling is kind of offline, and we are trying to now do online rolling process. So these are the different types of uh, issues. As I said, like, now the time has come probably for sustainable and, as a competitive manufacturing. It is important to see what is the exact service conditions, stresses a component will be subjected to. So if you just say Ti-6-4 and you need this much strength, maybe that day is now gone. So you have to see where the Ti-6-4 is using, what is the kind of service environment it will be subjected to, and do you need rolling for that, or you don't need rolling. I have now doing some work on nickel, where I'm finding that, I mean, it is Inconel 718, or say, ABD 900, which is alloy by design 900. So there are a lot of um, strength that you generate at 900 degrees centigrade and stuff. So if you have to age it and get that strength, then probably you need to roll it, because all these alloys like Inconel, maraging steel, I've referred to a paper on super duplex. So there also, your hardening phases are formed by atoms which doesn't diffuse easily. Like in aluminium, you see, because it is copper and aluminium, they generally develop the strength. It is quite straightforward, at least to achieve the strength without doing any rolling. You can get the strength, but in case of all the other alloys, I found it is very difficult to develop. So if you have a solution strengthened type of material, it is much easier as compared to a edge hardening alloy.
So Dr. Ganguly, Dr. Ganguly, there are some questions in the chat box. So we need a quick answer. If you can do that. So the question is that what is the recrystallization temperature for the alloy that you have considered?
Recrystallization temperature is for which alloy? Is it titanium or?
Yeah, so the alloy that you have deposited structures for that.
Okay, recrystallization temperature classically is like 0.4 to 0.5 times the capital T, which is basically melting point plus 273, and you do 0.4 times of it, and then, but that is a classical definition. Here, as I'm saying, I do not think there is a full-blown recrystallization is happening here. What is happening, because the thermal cycle is quite transient, because you're depositing another I'm talking about titanium now. So you're depositing another layer, and the thermal treatment is quite transient, but luckily it takes it to a temperature level of say over 880, which makes it to beta phase. So once it goes to the beta phase, with the cold working, we have basically prevented any epitaxial growth, and there is heterogeneous nucleation. So you generate lots of beta phase grain, which then subsequently cool to form alpha phase. So the structures that you have seen is basically the prior beta grains. So what I'm trying to say or emphasize in this work is that because of the cold rolling, you manage to break the epitaxial growth and forming equiax beta grains, which then transform to alpha.
So
sorry, for maraging steel and stuff, it is once again the same thing. I wouldn't say that it is completely recrystallizing. And to answer the question more in a focused manner, the recrystallization temperature will also depend upon the amount of cold work that is being done. So it is a kind of a dynamic thing. So as you have seen, like when we do 75 kilonewton rolling, it is creating finer grain structure as compared to when we do say 50 kilonewton rolling, and that is because of the fact that the formation of these nucleation sites during recrystallization will be different, because I'm assuming that the thermal energy is the same from the next pass or next layer deposition. So the thermal energy is same, but because of the rolling load was different, it is generating different amounts of nucleating sites for strain-free grades.
So last question, because of the time, we are already 9:48.
Yeah, I'm very sorry that you are. It's almost your bedtime now, I think. Yeah.
No. Just a quick answer from the. I'll pick up the last question. The cold working that you are recommending after warm. So does it have any effect on the residual stress the causing this?
Absolutely. It's a brilliant question. The first reference that I've shown, I think, so yes, we have done some measurements on residual stress and everything. So it will definitely have a residual impact on residual stress, but because it is cooling, if I roll and leave it, the residual stress will be vanished. Okay, so because there will be plastic deformation, and that will change the residual stress field completely. But when I do the next layer, the residual stress field will reform because of the fact that once again it has taken to a high temperature, and there from there it is cooling, and from there it is cooling, which will result in is once again in shrinkage stresses, and residual stress will form. So just if I can do the last rolling and don't do any further deposition, then you will see the residual stress is gone. Also, it will depend. Upon how much, what to call it. up to which depth or up to what depth the effect of rolling is reaching. So as the layer grows, so it is not, it will, I cannot say like if I do just on the top rolling, it will completely vanish the residual stress, because if then we have done some work on side rolling also, that can be an important factor. I found there is another question on fatigue testing, and yes, we have done lots of fatigue testing. I have loads of data on that, so I cannot. I mean,
so you can what I mean, it would be very nice that if we can share your papers and all, then I can circulate to the participants.
yeah, I will do that. So there are lots of work done on fatigue, and additive built structures are showing really good fatigue resistance once is done with rolling and interlayer rolling and stuff. They really showed very good fatigue crack growth resistance, and we did it on CT specimens, compact tension specimens across the layer, along the layer, different types, and it showed quite strong fatigue crack growth resistance.
Thank you. I mean, it's a wonderful the session that we had. Ganguly, it's a nice in this field. We have learned a lot, and thank you so much for your presence, and we are really honored. With this, I'd like to
Thanks very
close
much,
the session. But before we
Professor
close, before we close the session, I'd like to see that who are the speakers in Ananta. Yeah, thank you once again, Dr. Ganguly. So Ananta, quickly let us know the speakers for the subsequent. Yeah, this is the advertisement that the Center of Excellence is coming up with the 6 days training program on industrial robotics for the industrial people, and then also for the students and then staff members. This will be done from January 17 to January 22nd. So our next speakers are the Amit Thakkar from Infosys. The topic will be the connecting bridge between IT and manufacturing sectors. And then Professor Devdut Seat of IIT Kharagpur will be discussing about the machine vision for manufacturing. And then Feng Shu Gu from the University of Huddersfield in the UK will be talking about the sensing of the vibration for online process monitoring. This I'd like to close today's session. Thank you so much. And all webinars are getting recorded, so that which is also getting circulated across the participants and all. You can scan the code, and then you can also have it.
Thanks very much, Professor Paul. Yeah, it's always an honor to talk to you all.